Unexpected origins of the microwave oven. Percy Spencer, an engineer at Raytheon in 1945, was working on a magnetron for radar systems when he noticed something peculiar. He had been standing near an active tube while eating a chocolate bar in his pocket. The candy bar began to melt rapidly, sticking to his skin rather than remaining solid. Initially, Spencer assumed the heat came from ambient room temperature or perhaps a nearby heater, but the timing coincided exactly with the magnetron's operation. Curious, he took a bag of popcorn kernels and held them near the device. They popped almost instantly. He then tried an egg, which exploded in his face due to rapid steam expansion inside the shell. These experiments confirmed that high-frequency electromagnetic waves were generating heat within food molecules. The initial setup involved Spencer testing components for military radar during World War II, a time when technology was moving at breakneck speed. His discovery shifted from a minor annoyance of melted chocolate to a potential new method of cooking. This accidental finding led directly to the development of the first commercial microwave oven, which was originally massive and expensive, weighing over 700 pounds. The transition from a laboratory curiosity to a household staple took decades, but it all began with that simple, sticky chocolate bar on a hot summer day in Waltham, Massachusetts. Accidental discovery of penicillin. Alexander Fleming returned to his laboratory at St. Mary's Hospital in London after a vacation in August 1928, expecting to find a tidy workspace filled with bacterial cultures. Instead, he found a petri dish containing Staphylococcus bacteria that had been left on a bench near an open window. The lid was not perfectly sealed, allowing mold spores from the air to settle inside. Fleming noticed a clear zone around a specific patch of blue-green mold where the bacteria seemed to have dissolved or died off. Most scientists would have discarded this contaminated dish as a failure, but Fleming recognized that something in the mold was producing an antibacterial substance. He identified the mold as Penicillium notidum and began isolating the active agent. The setup involved a messy lab environment typical of the early 20th century, where researchers often worked with multiple cultures simultaneously without strict sterile protocols. This incident broke the status quo of bacterial treatment, which relied heavily on antiseptics that killed both good and bad bacteria. Fleming's observation was not a planned experiment, but a result of neglecting to clean his workspace thoroughly. The discovery marked a turning point in medical history, leading to the mass production of antibiotics during World War II. While Fleming did not initially understand how to stabilize the compound for long-term use, his accidental finding laid the foundation for one of the most significant medical advancements in human history. Vulcanized rubber's heat-induced transformation. In 1839, Charles Goodyear was struggling to create a rubber product that could withstand temperature changes without becoming sticky or brittle. He had been experimenting with various additives to improve the durability of natural latex. One afternoon in his small workshop in New Haven, Connecticut, he accidentally dropped a mixture of rubber and sulfur onto a hot stove while testing its properties. The heat caused the mixture to turn into a tough, elastic material that did not melt or stick when touched. Goodyear had been trying to solve the problem of rubber's instability for years, but this specific incident occurred purely by chance during a routine heating test. Before this discovery, rubber items would disintegrate in summer heat and crack in winter cold, limiting their utility significantly. The setup involved a chaotic workshop filled with various chemical compounds and unrefined latex samples. Goodyear spent the next several years refining the process, which he called vulcanization, to make it consistent for industrial use. This accidental event transformed rubber from a seasonal novelty into a vital material for tires, hoses, and waterproof clothing. The discovery was not immediately recognized as revolutionary. It took time for manufacturers to adopt the new method, but once they did, the impact on transportation and industry was profound. Post-it notes weak adhesive. In 1968, Spencer Silver, a chemist at 3M in Minnesota, was attempting to create an ultra-strong adhesive for use in aerospace applications. He mixed various chemicals in his lab, hoping to produce a bond that could hold heavy materials together permanently. Instead of achieving the desired strength, he created a glue that was surprisingly weak and tacky, allowing it to be peeled off surfaces without leaving residue or damaging them. For years, this failed adhesive sat on his shelf, unused because it did not meet the original criteria for success. The setup involved a typical corporate research environment where failure was often viewed as a setback rather than an opportunity. It was not until 1974 that another 3M employee, Art Fry, found a practical use for Silver's creation while singing in his church choir. Fry needed a way to mark pages in his hymn book without the bookmarks falling out or tearing the paper. He applied silver's weak adhesive to small pieces of paper and realized they could be repositioned easily. This accidental discovery led to the development of Post-it notes, which became one of 3M's most successful products. The story highlights how a product deemed a failure in its intended context can find immense success when repurposed for a different need. X-rays phosphorescent screen. In November 1895, Wilhelm Röntgen was conducting experiments with cathode rays in his laboratory at the University of Würzburg. He had covered a glass tube with black cardboard to block out visible light while testing how these invisible rays traveled through different materials. One evening, he noticed that a screen coated with barium platinocyanide on a nearby table began to glow brightly, even though it was several feet away from the covered tube. The glow appeared only when the tube was active, suggesting that some form of radiation was passing through the cardboard and hitting the screen. Röntgen spent weeks investigating this phenomenon, realizing he had discovered a new type of ray that could penetrate soft tissue but be blocked by denser materials like bone. The setup involved a darkened room where Röntgen worked late into the night, often forgetting to eat or sleep while observing these mysterious effects. He took the first X-ray image of his wife's hand, revealing her bones and wedding ring clearly against the film. This accidental observation revolutionized medicine by allowing doctors to see inside the human body without surgery. The discovery was not planned. Röntgen simply noticed an anomaly in his experimental setup that others might have overlooked. Silk Road silk from mulberry leaves. While the exact moment of silk production is debated, historical accounts suggest it began as a result of observing silkworms feeding on mulberry leaves. Legend states that Lezu, the wife of the Yellow Emperor in ancient China, around 2700 BCE, was drinking tea under a tree when a cocoon fell into her cup. As she stirred the hot water to cool it down, the silk thread began to unravel from the cocoon, revealing its length and strength. This accidental discovery changed the course of textile history, leading to the domestication of silkworms and the creation of a fabric that became highly prized across Asia and Europe. The setup involved a royal garden where Lezu was enjoying a quiet afternoon, unaware that her teacup would become the catalyst for an entire industry. Before this event, textiles were made from wool, linen, or cotton, none of which possessed the luster and strength of silk. The process required careful observation of the silkworm's life cycle, but the initial breakthrough was purely serendipitous. The discovery led to the Silk Road trade routes, connecting China with Rome and other civilizations. While some details are mythological, the core narrative reflects a genuine historical progression from accidental observation to systematic production. Potato chips thin slicing technique. In 1853, George Crumb, a chef at Moon's Lake House in Saratoga Springs, New York, was preparing dinner for a customer who complained that his fried potatoes were too thick and soggy. Frustrated by the repeated complaints, Crumb decided to slice the potatoes paper thin and fry them until they were crisp and brittle. He intended to serve this dish as a joke, expecting the customer to reject it due to its unusual texture. However, the customer loved the thin, crispy slices, calling them Saratoga chips. The setup involved a busy restaurant kitchen where Crumb was trying to satisfy a difficult diner who had sent back multiple orders of fried potatoes. This accidental creation was not part of any planned menu but rather a reaction to frustration and culinary experimentation. The discovery led to the mass production of potato chips, which eventually became a global snack food industry worth billions of dollars. While some historians argue that Crumb's wife might have been the actual inventor, the story remains consistent with the narrative of accidental innovation in response to customer dissatisfaction. Concrete's hydraulic setting. In ancient times, Romans used a mixture of lime and volcanic ash to create a durable building material known as concrete. However, the exact formula was lost after the fall of Rome until John Smeaton rediscovered it in 1756 while rebuilding the Eddystone Lighthouse off the coast of England. Smeaton needed a material that could set under water without dissolving, but traditional lime mortar failed under constant water exposure. He experimented with various additives and discovered that adding crushed limestone to the mixture created a hydraulic cement that hardened when exposed to water. This accidental discovery was not a single event, but rather a series of trials where Smeaton tested different ratios of ingredients until he found one that worked. The setup involved a construction site in a harsh coastal environment where traditional methods were failing repeatedly. His breakthrough allowed for the construction of durable structures like bridges, harbors, and dams that could withstand water pressure. This discovery laid the foundation for modern concrete, which is now the most widely used building material on Earth. Styrofoam's expanded polystyrene. In 1941, Erich Stauffer was working at a factory in Germany where he was trying to create a lightweight plastic for insulation. He mixed polystyrene with a blowing agent and heated the mixture, expecting it to melt into a solid block. Instead, the heat caused the material to expand rapidly, creating a foam-like structure filled with tiny air pockets. Stauffer initially thought the batch had been ruined due to overexpansion, but he realized that this new material was incredibly lightweight and provided excellent thermal insulation. The setup involved an industrial manufacturing process where precision was key, yet the accidental expansion led to a completely different product category. This discovery revolutionized packaging, construction, and food service industries by providing a cheap, durable, and insulating material. Styrofoam became ubiquitous in everything from coffee cups to building insulation. While the initial experiment was meant for solid plastic, the accidental foam structure proved far more versatile than originally intended. Velcro's hook and loop mechanism. In 1941, Swiss engineer George de Mestral went hiking with his dog through the woods of Switzerland. After returning home, he noticed that burrs from the cocklebur plant had stuck to both his wool trousers and his dog's fur. Intrigued by how these small hooks clung so effectively to fabric loops, he examined them under a microscope. He saw that each burr had tiny hooks that caught onto the loops of the material, creating a strong bond that could be separated with effort. De Mestral spent years trying to replicate this mechanism using synthetic materials like nylon and cotton. The setup involved a simple nature walk where de Mestral was observing his dog's behavior rather than conducting a formal experiment. His accidental discovery led to the invention of Velcro, which is now used in everything from aerospace suits to children's shoes. The story highlights how observation of natural phenomena can lead to technological breakthroughs that solve complex engineering problems.